So what's up guys, in this video I'm actually going to show you how to make a whistle detector. So the whistle detector will, using traditional techniques, detect a sequence for whistles within a given time period. So I'll demonstrate. So if you do like, it will respond, but if it use a different cadence, like, once you have that those 3 beat cadence within a time period, it will detect it. It's very resilient. Other types of noise and tapping and stuff, it will only respond to the frequency that of your whistle, and with particular beats within a particular time period of your whistle. And if it's too slow or it's too fast, it won't work. So in this video I'll actually show you how we can do that. So guys, this is the actual circuit. So the circuit is divided in a number of stages. In the first stage, we have the microphone here. This is the stage 1, the microphone with the biasing stage. So this is actually an electret mic, and we have this 47K resistor here, R1, that actually provides a bias to the microphone. And then we have the C1, at 22 nanofarad, and that's for AC coupling, so it will remove any DC and pass only the audio signals, vibrations or sound, or whatever it is, we want to get to go to the other stages. And once we have that signal coming out, what you want to do is you want to actually have an amplification stage. So I actually use the 2N to the 904 transistor here, and that is acting as our amplifier. Now I saw some circuits, you look at a lot of amplification circuits, things like clap on, clap off, or other sound detector circuits. They typically is a up amp. But because I want to keep the bump cost low and ensure that it works properly with the 3.3 volts in a lot of circuits, use the LM358s or the LM324s, and they don't work well with 3.3 volts. So yes, I have op amps like the MCP, have the 602, the 6022 and stuff that are rail to rail, but the transistor is really low cost, and using a 10-cent MCU, so keep the cost as low as possible, right? So the transistor is the amplification here, and this R3 is actually providing bias to the base AQ1, ensuring the transistor is operating in the active region. We have R2 here also that's acting as a pull-up that actually supplies power to the collector of the transistor. Now, once we get our input and amplify it, the next thing we have to do is we actually have to perform envelope detection, what you call peak detection. And if you look at clap on, clap off circuits and sound detector circuits, they typically use the same type of setup. So what we have is we have another 10F capacitor here, and that will block any DC from the amplifier output. And what you should get on the output here is a clean sound wave. And we have D2, right? This is a diode that will actually rectify the signal and only allow positive peaks to pass through. And D1 is actually a protection diode to clamp the reverse polarity spikes in the circuit. Then we have this C3 here, this one microfarad capacitor, and actually holds the peak voltage for a short time. This is the actual envelope detection part here, because this capacitor will actually hold the peak voltage, and then R4, this 100K, will actually discharge slowly, to actually track the envelope. It's essentially setting, the envelope decay rate, so the rate at which the capacitor discharges. So this part will actually convert the AC signal into a DC-like envelope that actually represents the sound intensity. I could dive deeper into this if you guys want, probably the oscilloscope and show you, but that's what's happening. I tested on the scope and actually see the peaks, as a DC voltage. And that now is fed into the microcontroller, which is actually performing signal sampling. So the microcontroller it's connected to the envelope output, and it's sampling this with the ADC to detect the loud songs, which in this case is whistles. And the threshold we set on ADC for whistles. Now this circuit it easily modified to do, clap or any type of song. You just have to experiment with the song you're trying to detect or even your whistle frequency. What is the actual ADC threshold trigger? You have to manually determine that. What I actually did is actually take this output, hook it up to the oscilloscope, and look at the when I whistle, for the frequency range I'm looking at for whistling, what was the threshold, and I used that to set, the threshold in the ADC and the microcontroller. And this actually does interfaces, on analog audio into digital domain for the whistle detection. We could have used something like a comparator here too, but that will be extra space. Actually try to use the comparator on this microcontroller, but the documentation, even though it was helpful, I followed documentation, I was not able to use the comparator function of the CH32V, and the examples by WCH weren't working, but that's okay because we didn't really need it. We could use the ADC sampling, but you could also use a comparator, if you're doing clapping and stuff, according to the type of song signal you're trying to detect, a comparator might work better. Then we have PC0, that is the output here, and this is actually that's a LED indicator. Of course, we have the 1K to limit the current out the pin, and when a match occurs, it will just flash the LED. So this is the circuit. It's a simple circuit, but at the same time, you have to kind of tweak it according to your song. So, this is in the envelope part here is where you really will tweak, according to the value of R4 and, C3, you kind of, um, control the response time of the circuit, and then when the microcontroller filtering will kind of help with the threshold for sound. So we can actually walk through the software. In the software, I actually have the ADC threshold 90 was, where it was for my the song frequency I was trying to detect. I looking at 3 target counts. You could have 1, 2, 3, peaks detected, and you actually have the millis counter. So I actually use the timer and microcontroller for doing counting the amount of milliseconds. I have a timer interrupt. This millis function, this returns the count. I use UART for some debugging, and of course functions to send string and send integer values. Initialize GPIO, we initialize the ADC, we read the ADC, we initialize the timer, and then in the main we just first I just test if the timer is working, and then we have our pulse count, and the first pulse time, and in the main loop is where we actually have the testing taking place for the actual function to work. So we actually, at the beginning of the loop, we start looking at the timer. If the timer window is expired, since the first pulse we detect, we actually put the window expire. So that way, it won't be storing pulses over time. It will just store, the sequence of pulses we're looking at. We then do the ADC sampling and, record the time of the first pulse in the sequence. And, if we reach the target count within the time window, then we toggle the LED. If it's too slow, the window will expire, and then, we'll reset after reaching the target. That'll be success or failure. And, we just do a check for if the ADC is less than the threshold, and we have a 10 millisecond loop. So that's it, guys. That's what this, how we do the circuit and the, the firmware for this particular project. Is a nice project, and I hope you find this video useful. Be sure to like and subscribe. Thanks for watching.